Hello and welcome, and this is just a continuation of our revision series. And here we'll just quickly go through this chapter 4, which is about differential amplifier. And again, we won't discuss too much of the basics, and like we are assuming that you are familiar with this chapter, and it is just a short video where just we'll quickly skim through this chapter. Okay. So thus we already know that what is the need of differential signaling, why do we need differential amplifiers, and just here, I would just recall, which is also given in Razavi, that is if you just sketch a basic differential amplifier, which and this in this case this is actually a pseudo differential amplifier where we are not having a common tail current source to tie these two ends together. So why is this guy not used as such? So this guy is not used as such is because here the GM is a strong function of the common mode signal, which is basically the bias signal, which is something we typically don't want, right? And thus we basically use a tail current source at the bottom, and this guy is now fixed when we use a tail current source at the bottom. And now, by using a fixed tail current source, let us call it I bias, now at any point of time in the operation of this circuit, the summation of the current through this and this branch is a constant, and thus basically we are able to make the GM or the transconductance of this pair very loosely or rather independent of V in CM, which is typically desirable in the operation of a circuit, right? And why and what is that? So it's not something I'm going to elaborate upon because it is just a basic and a very quick revision, right? Okay. So let us move on to the next topic where he basically takes us to the basic fully differential pair, which is basically this circuit only, which I have drawn above. And since this is circuit's basic motive is to amplify signals, so we'll talk about the small signal analysis real quick. Also, what is fully differential pair? Fully differential pair basically means that I'm taking output the difference of output at these two ends, right? And it would have been a simple differential simple differential or single-ended differential amplifier if I would have been if I would have had taken output from either of the terminals, like only one terminal. But in fully differential amplifier, I am taking the difference of output at these two terminals. And we are already able to appreciate this fact, and I think we already should be able to know this if I am to differentiate between these two between a single-ended differential amplifier and fully differential amplifier. The basic difference come here is that in both of these cases we are enjoying the benefits of differential signaling, which is basically common mode rejection. But the thing here is that the differential gain here is basically half of the differential gain fully of the fully differential amplifier. The gain in single ended is half, and I think we can understand it intuitively also, because here you are basically taking only one end as output, and here you are taking the difference of the outputs which are themselves differential in nature. So you can understand that the swing will be twice, right? And thus the gain here is also twice. So that is the basic intuitive explanation. But typically we find single-ended differential amplifiers more in use because, for example, we know that the output of this particular amplifier will go into some other block, right? Maybe a ADC or whatever. So the thing here is that these blocks also have only one-ended inputs, which means that the another terminal of the signal is by default assumed ground, right? So typically we use single-ended differential amplifier also because they require lesser bias current, consume lesser power in area. Here you also need common mode feedback and all, although it is not covered in this chapter of Razavi. But yeah, and since here for transmitting fully differential amplified signal, you need two lines, and typically the blocks which you will feed it to will be single-ended only. So you need now that you have to convert this two-line signal into a single line signal. So all these extra circuitry might also be required. So typically we use or we find usage of single-ended differential amplifier, although these are also in use. But that's the basic difference and basic idea that what is single-ended amplifier and what is a fully differential amplifier. Great. Now let us talk for just so that we are more general in our approach for time being, and also as per it is given in Razavi's book, we'll analyze quickly analyze a basic fully differential pair, and again to gain intuition we will ignore the body effect, and we'll also ignore the channel length modulation, and we'll just try that we are to quickly analyze this circuit. And since it is the incremental model, so you know that the current source at the bottom will be open, right? So this is what we'll observe. And again, since here it is the incremental model, which means we can apply superposition. So what we'll do is we'll apply one input at a time and try to see that what our output is. Okay. So let us try to find what is V out one due to first this input and then due to this input. Okay. So now due to this input, if you try to see how what will be the signal here due to V in one. I think we can already imagine that this is just a CS stage, and we have to just now find that what is the resistance looking through this path, right? And through this path, we already know from our previous revisions also that the impedance through this path is 1 by GM. Assuming that this circuit is symmetrical and these two transistor sizes GMs are equal, so we can just directly write from the formula of a degenerated CS stage, which is given by GM times R, if I'm saying the resistor values are RR, plus 1 plus GM by GM, where 1 by GM is the resistance through seen from the source of this way, right? And I'll just multiply it by V in 1. And now I have to say that what is the signal at V out 1 terminal due to V in 2 when V in 1 is grounded, okay? So now if I'm applying V into over here, the signal that I'll see here, and then the signal which I'll see here. So if you are able to understand this, what is basically happening is that in the small signal model, when this guy is shorted, first V into will appear here through a source follower stage, right? So we have to write the formula of the source follower. So source follower's formula is what? It is just Gm times resistance seen at the source, which is again 1 by Gm plus Gm plus resistance seen at source. So this is one stage. And now whatever signal that appeared here will now pass through this guy. And this is a common gate stage. And again, in the small signal, the gain of this will be what? Gm times R, right? So we'll just multiply it by Gm times R. And this is our signal, Vn2. And again, just by symmetry, we can easily comment that if V out 1 is this, first let us just simplify this expression so we are able to make sense of it. So Gm by Gm, so it is basically GMR by 2, right? So it is GMR by 2 times V in 1. And this guy becomes again 1 GMR by 2. So again, so this is a great scenario for us that things simplify quite easily, and this guy becomes GM R by 2 times V into. So again, intuitively we can say that when I'm trying to check for V out 2, it will be just a similar scenario. So what I'll have is that minus GMR by 2 V into, and I'll have GM R by 2 V in 1. And now, since my agenda was to find the differential gain of this guy, so I'll just subtract these two signals. So what I'll get is del V out. Yeah, so I'll get del V out is equals to what? These V in 1 can be made common, and what I'll get is minus. I can take minus in this whole guy. I can just take the minus common. So what I'll have is it looks like V in 1, and since I'm taking it all as common, okay. So what I'll get is I'm subtracting. So yeah, V out 1 and GMR by 2. And so now if we just mentally solve it, we can easily conclude. What can we conclude? That